Hello everyone, this is Firoz Nadav. In this video, I am going to talk about assumptions in working stress method regarding design of flexural members. Flexural members are beams and slabs are called as flexural members because the flexure, the bending moment, is the predominant internal forces in the beams and the slabs. So that is why first the beams and the slabs are primarily designed for the flexures, and then in some cases shear is also predominant, but in most of the cases of beams and the slabs, the predominant forces are the flexure, the bending moment. Okay, so this is the first assumption in WSM philosophy with regards to flexural members. Plane section before bending remains plane after bending. It is also the very first assumption in LSM philosophy with respect to flexural members. You see, this assumption is talking about uh, the cross section of the beam. What happens to the cross section of the beam before and after bending? So here I will draw the longitudinal section of the beam, and you can say that it is before bending. After the application of the load, what happens to this beam? It bends in this way. So this is the final profile of the beam after bending. Okay. So you see, before bending, the cross section, it is plane. Naturally it is plane, and something will happen to this cross section after bending. So after bending, what happens to the cross section? The cross section is distorted. The shape of the cross section is changed, but it does remain plane. It is not a curved surface, it is a plane surface. So this is what is the cross section after bending. So this is what is the assumption: before bending, after bending, it remains plane. And one more thing we can derive from this assumption: the distribution of strain is linear. I will name here, it is A B. This is AB before bending, and after bending it is A dash B dash. Okay, so I will draw one line. This is AB before bending, and after bending it becomes inclined, A dash B dash. Okay. So you see here, the distribution of the strain is linear. This is the point of neutral axis wherein you don't have any strain. Above neutral axis, the section is subjected to compression, and below neutral axis, the section is subjected to tension, but the distribution of the strain is straight line. Linear means the distribution is straight line. Okay, this is what we can learn from this assumption. The distribution of the strain is linear, it is a straight line. Okay, here we have second assumption, which says all the tensile stresses are taken up by reinforcement and none by concrete. And by the way, this assumption is true in all of the design philosophies. In LSM, in ULM, we take this assumption. We say that concrete is not capable of taking the tension. So all the tensile stresses are taken by reinforcement, are taken by steel. Okay. So you see, this assumption, it goes by the basic properties of the concrete. Concrete by nature, it's a brittle material. Okay. So any brittle material will not take any tensile stresses. But we do have some tensile stresses of the concrete. We do have some tensile strength of the concrete. For example, for M20, you see, we have tensile stresses up to 3 to 4 megapascal of concrete. And you see, this uh, tensile strength of the concrete is not adequate to take the tensile stresses in the structures. Okay. So you see, when you are talking about the structures, when you are dealing with the design of structures, you get two kinds of stresses: tensile stresses as well as compression stresses. Okay, so what we say, concrete will take all the compression. Since concrete is weak in tension, so the tensile stresses will be taken by steel. That is what is the purpose of employing steel in RCC structure, to take the tension of the structure. Okay. One more thing that we have to learn here, we also have to see what happens to the stress distribution diagram by this assumption. Okay. So I will draw the section of the beam here. I will draw a section of the beam, and we are assuming that the beam is sagging. When the beam is sagging, this happens to the longitudinal section of the beam. This will be the neutral axis. Below neutral axis you have tension, and above neutral axis you have compression. Okay, so this is the neutral axis that I am drawing here. Okay, so below neutral axis you have to show the bars, the reinforcement that will take the tension. Okay, so above neutral axis you don't need bars, but you provide bars. Okay, I will tell you why you provide bars, but here you don't need bars, right? So you see, below neutral axis the section is subjected to tension, and we say all the tensile stresses are taken by steel. And here we are showing sigma st. Sigma st is shown at a point where steel is introduced. Okay, so you see you have concrete here. Below neutral axis you have concrete, and this concrete, they are not taking any tensile stresses. All the tensile stresses are taken by this steel. That is why we show sigma st, which is stress in the steel. We show at a point where steel is introduced. Okay, so above neutral axis you have compression, and we say that all the compressions are taken by concrete. Okay, so as you at a point of neutral axis the stress are zero. So as you go above from the neutral axis the stress is increasing. Okay, so you are showing the stress distribution diagram right from here. You're drawing some diagram from this point because you have concrete. Above neutral axis you have concrete, and all the concretes are taking the compression. But here you are not drawing any diagram. Directly you are showing the stress at a point where steel is introduced. Okay, so this is what we learn from this assumption. Okay, so here we have the third assumption, that is the stress strain relationship of concrete and steel are linear under working load. Now, whenever you want to see the behavior of any material, what you have to do, you have to put that material into test and draw the stress strain curve. Okay, so we have two material in RCC, concrete and steel, and one more thing you see in WSM, everything is linear with respect to material. Everything is linear. We will talk about that. Okay, so you have to put the material into test and draw the stress strain curve of that material. When you see the stress strain curve of that material, you depict the behavior of that material. You see the behavior of that material, and you can judge how the material will behave under some load. Okay, so what it says, for concrete the stress strain curve is linear means straight line, and also for steel the stress strain curve is linear, it's a straight line. This is for concrete and this is for steel. It says for both the material the stress strain curve is linear, it is a straight line. Okay, so one of the reason why why WSM method is criticized, you see, it does not depict the exact behavior of concrete. We can say there is some linearity in the initial phase of the steel, but it is up to some extent. But you see, concrete is highly non-linear material, and saying that the concrete is having straight line, stress strain curve of concrete is straight line is not exactly depicting the behavior of concrete. So that is why we have the advent of other philosophies. In LSM we have tried to show the actual behavior of the concrete. So we will talk about that when we study the LSM philosophy. So here the assumption is that the stress strain curve under working load is linear. Okay, so under working load, see, beyond working load you have the ultimate load. So we have an indirect message here. At the ultimate load the stress strain curve will not be linear. We can take indirect message also, but under working load it is linear, it is straight line. Assumption number 4, it says there is a perfect bond between concrete and steel. You see, when we put the steel in RCC beam or in any RCC element, we have to ensure that there is a perfect bond between concrete and steel. Okay, why we have to ensure perfect bond between concrete and steel? You see, when the RCC element is subjected to load, there is a transfer of stress from concrete to steel or from steel to concrete. We have to ensure the transfer of stresses from concrete to steel or steel to concrete, and it can be done when you have a perfect bond between these two material. If there is no perfect bond, so what will happen? Under the load, the steel will slip, and when it slips, there is no transfer of stresses between these materials. Assumption number 5, the modular ratio M equal to 280 by 3 sigma CBC, where sigma CBC is permissible stress in the concrete. They are telling us to use modular ratio when we use WSM philosophy. Okay, so what is modular ratio? It defines you the compatibility between the concrete and steel. It gives you the relation between concrete and steel when we are using WSM philosophy. Literally speaking, the formula of modular ratio is, it's a ratio of Young's modulus of steel by Young's modulus of concrete. This is the formula, this is the definition. Okay, so why we are switching from this formula to this formula? Okay, so in the long run, you see, concrete is subjected to long term deflection. Long term deflection. When you are interested in short term deflection, in short term behavior, you can use this formula, M equal to Young's modulus of steel by Young's modulus of concrete, and it will give something related to short term duration. See, when we are talking about the age of the structure, we have to see long term deflection, and it is called as creep of the concrete. Creep of the concrete. Okay, to consider creep of the concrete, IS 456-2000 has given the formula of modular ratio, and this formula is the empirical formula, means it cannot be derived. It is based on n number of tests. So we have to use this formula, and we have completed the assumption in WSM philosophy with respect to the flexural member. Thank you everyone for watching this video. Thank you very much.